All right, couple of announcements. First of all, for the folks that are online, sometimes I don't see if you put something in chat. So feel free to just interrupt me and yell and get my attention or whatever if you have a question. I promise I won't be offended. Couple other things. For your papers that were due, I don't know, was it due earlier this week or last week, whatever it was. When you go and look at them, I graded them more picky than I typically grade, with the purpose. First of all, keep in mind that most of your grade in this class is exams, so it's not going to hurt your grade at all. But one thing I want to try to get you transitioned towards is, and something that high schools have more over the last decade, let's say, become worse and worse at doing, is preparing you for kind of research and writing. So hopefully you look at some of that feedback and gather some ways to improve your writing. There won't be tons of writing in my classes, but since we're front heavy on non-programming stuff, that's kind of why we're filling in some writing. So hopefully that gives you some things that will help you in some of your other classes, but don't worry too much about your grade. Like I said, you're going to have a ton of homework assignments with the programming assignments, and it's not worth a huge amount of your score. It's really about training you for the exams. And remember, I have the policy on the exams where if you bomb the midterm and do better on the final, I'll replace your midterm exam grade with whatever you got on the final. So ultimately, homework is practice for the big game. So if you're typically a straight A student and you got a 60 on the paper or something, don't freak out. Your grade is fine. All right. I just happen to spend a little extra time on it for some feedback. Okay, we got it. All right. Another thing, so I'll go ahead and talk about this now, just because I've had several people come up. So first of all, the stuff we've been talking about up to this point, largely I'm not going to test you on. So you might say, well, why are we wasting our time on it? So the example I use is it's kind of like building a house. We need to pour a solid foundation before we get into some of these other things. So I know I'm assuming none of you have had programming. I'm also assuming that a lot of the stuff we've talked about in here over the last 2 weeks, let's say, are things that maybe none of you have seen before. So like, last class, we were talking about things like JSON and XML, and, we're throwing all these terms around, and these things can get easily lost in translation. But I promise you, this foundation here is going to start making more and more sense over the next 2 or 3 years of school, as you start writing programs that communicate with each other using JSON. Like, oh, that's what that's for. But we're trying to paint a picture of the things that you're already used to dealing with. I mean, if you just think about the last week, we've really been painting the picture of how technology has mimicked McDonald's, the client server model. You walk in, I want a Big Mac, they hand you a Big Mac. Your browser says, I want page XYZ. The server hands you the page XYZ. We just talked more about what's that language they're talking about in the middle, because we choose English when we walk into McDonald's, right? Computers aren't so hot with that. So we're really trying to, I guess the point I'm really trying to get across is that the things that we imagine in technology as being very cryptic and difficult and, beyond our understanding or something like that, in almost every case is fairly simple stuff that just mimics how human beings already do things. But until we break down that wall and see that and kind of get past, I think I even said it last class, that a lot of these new technologies that come out, especially with web programming stuff, almost every one of them has some cool sounding, easy to market name or something like that. They're all just JavaScript libraries, just a fancy name for something that's existed for 15, 20 years. All right. So, and maybe they just do one thing a little bit better than they did before, or something like that. All right. So if at this point, some of these things are kind of flying over your head, or you feel overwhelmed or confused, that's probably about where you should be. It's okay. as we get into the coding stuff and start integrating some of this stuff. A lot of it we won't even integrate right away. We're not going to be writing a network aware program right off the bat. All right, but having this stuff kind of in our back pocket and understanding the role that the software we write might play. Because one thing I want all of you to start thinking about at some point once you start getting some of these skills is not so much, oh, can I write an app for the iPhone or for Android and put it up in the store and make money? But, oh, are there aspects of things that I do on my computer that I can automate by writing my own program to do it? For example, because that's what computer programming is. It's telling this computer to do something. So realistically, anything you can do by hand on the computer, there's legitimate potential that you could write a software to at least in part automate that. Make sense? And sometimes, I think I used the example last time about years ago, I wrote a stock quote application for iPhone. And I needed to get my data from somewhere because my program didn't know what the current stock price of Apple was or something like that. So it had to go out and get that data from somewhere. And at that point in time, we didn't have these things called APIs that fed us information, that were there to be information providers with consistent ways of talking to them. So my only option was to say, oh, well, I know I can go onto a web browser and I can browse to a couple different sites and get the current stock price. So I'm going to write a program that mimics that hits this website and gets this wall of HTML. And then I'm going to go through and I'm going to pick out that piece of information from this wall of HTML that I'm actually interested in showing on my screen on my app. Does that make sense? That's not the way you do it today. These programs are typically called screen scrapers. There's all sorts of libraries out there for different programming languages that allow you to conveniently screen scrape stuff. So, but in any case, just kind of understand that most of what we've talked about in the last couple of classes has really been the data that feeds our programs. Where does that data come from? Because almost every program that you use today is some view into a data source somewhere. You check your email. Well, that email isn't stored on your computer. You're getting it from somewhere up in the cloud. Maybe it creates a copy on your computer, but that's not where it's looking for it, right? It's communicating with your Concordia emails, communicating with Concordia's email servers, which is Office 365, and authenticating you, downloading the stuff from the Exchange server, yada, yada, yada. And then you're viewing it through your email client on your computer or on your phone or whatever it is. But behind the scenes, that software had to communicate over the internet to get that information. Make sense? So from our perspective, it's kind of like making a phone call, except the person on the other end of the phone isn't speaking English, right? They're speaking some agreed upon protocol, for instance, like the HTTP protocol. Or in our more modern stuff, they're probably deciding, okay, you send me questions in some sort of JSON format, I'll spit back the result in a JSON format. And if you remember from last class, we looked at some examples. So here's XML and here's JSON. So here's that same data in XML represented in JSON. So this isn't about you learning XML or you learning JSON. It's more about looking at that and saying, oh, I get it. If I'm a computer program and somebody sent me a string that looked like that, do I feel like, even as a human being looking at that, I can pretty much immediately tell that that's holding a first name and a last name, Mike Littman, right? And we can imagine that a computer program could take that and somehow extract the Mike and extract the Littman piece, right? That feels like that is an easier job to do than the piece up here, which again, as a human being, we can look at that and after a few seconds see that, oh, those same pieces of information are there, but we imagine that that seems a little bit more cryptic to get at that information, right? As a human being, we can pick it out because we're smart. But if you had to write a computer program that went through and processed this line and ultimately extracted this guy and this guy, it's not hard software to write, but it is more complicated than this software and less featureful. So we would probably call JSON an upgrade to XML in terms of the communication protocol or the communication language that a program speaks to, a client speaks to a server, a program speaks to a server somewhere. All right, makes some sense? All right. So again, these things kind of confuse you, fly over your head. Ask a question. When I say, you know, does this make sense? It's not rhetorical. If it doesn't, feel free to say, I have no idea what you're talking about. Maybe I say that's okay. Just hang with it and we'll see when it makes some sense, or I can give you a different example or something. Otherwise, so the expectation is some of this stuff might feel fairly vague right now because you really don't have some of the details you need to truly incorporate it into problem solving. Because at this point, you haven't started solving problems with this data. I'm introducing you to these ideas, but you haven't actually utilized those to do anything. And certainly you're not learning tons when you open up a web browser and Google something. You've been doing that for years and years and years. Now you're just seeing what's actually happening behind the scenes. Even now, you're not going to have to do that because your web browser does the HTTP thing for you. So you're still just typing stuff up and hitting search, right? And it sends the stuff and it magically works. I'm just showing you what's behind the scenes a little bit. All right. All right, so let's swing back towards programming languages. Again, we actually haven't gone away from that at any point, and you'll see what I mean by that sooner rather than later, I guess. So if you remember, we had another slide that says there's 3 kinds of programming languages. We have machine learning, we have machine language, we have low-level languages, and we have high-level languages. So machine language is zeros and ones. That's the language that this computer ultimately speaks under the hood, right? And I made the joke, you know, we're not built for the 2-button keyboard, right? Low-level language, we looked at that hello world Linux language that even leveraged the operating system to do some power tool type stuff. So even though it looked cryptic to us, it should be far more cryptic. That same program 40 years ago would have looked much more cryptic because it wouldn't have had these special tools built into our modern operating systems to do some of that heavy lifting for us. We would have had to write the low-level code to do that too, which I promise you really sucks. All right. Thirdly, we have high-level languages, and that's what we like. Well, that's what we like better than the other 2. Once we get into programming, you start actually writing code, you're going to pretty quickly, I mean, I want all of you to stick it out because I've told you several times already, I'll say it again now, programming is hard and you're not going to be very good at it at first. But I want you to view it a lot like a sport where you have to put in the reps, you have to miss shots, whatever, over and over and over again until you get some competency. All right, you know, you can't just go to Michael Jordan's basketball camp and be ready for the NBA. You may have academically learned a bunch of stuff, but until you've shot 10 million jump shots, you're not going to be at that level. All right, programming is going to be similar. Where you see me do it, you will much more quickly understand correct answers when you see it than be able to write it yourself. Even pretty simple stuff. Okay. And then you're going to get frustrated when you're actually writing the code that, you know, you'll have a program that's 8 lines of code and you have 200 errors. Like, how is that even possible? You know, and usually it's one error that just caused this flow through of additional problems. But you'll learn pretty quickly how important case sensitivity is, how important a semicolon at the end of the line is, you know, opening and closing curly braces are in some of these languages, that kind of stuff. So there is a structure to the language that is very important. Computers are significantly more, let's say, precise than us from the perspective of when we give instructions to a computer, it's not like a human being. It can't fill in the gaps, right? It can't interpret what you probably meant. You got to tell it what you really mean in order for it to solve those problems. And that requires us to stick to a very rigid structure. And that's going to be uncomfortable at first for most of you. Again, some of you do have some programming background. So sometimes I'll ask questions like, how many of you have written something in this language or whatever. with the expectation that maybe there was a couple of people in here who had a programming class in high school or something. But my assumption is that none of you have written a line of line of code before. Okay, so I suspect that 75% of this class probably fits that bill, at least. But that's the assumption I make. So some of you had some programming before. You may have an advantage in that you already have some experience, but you may also have a disadvantage in that you also have some bad habits. All right. So, because one problem with learning programming in today's world, because and this is kind of why I go under the hood so much, some of the tools that we have today do so much of the work for you that you aren't actually using much critical thinking to solve the problem. You just click 2 or 3 buttons and it's solving the problem. Now, if your goal ultimately is just to get it done and move on with life, that's fine. But you're all computer science majors or something related to computer programming that you're going to use in your job. Well, sometimes you're going to be asked to solve problems that other people have not necessarily previously solved. You're going to need the tools to write your own custom stuff. You can think of yourself as kind of like one of those custom carpenters where, they have to, you're building a house and you have some weird structure that you need them to create. So they're in there and it's like a one-off type of custom carpentry job. Make sense? You're not going to Home Depot and buying, 600 of the prefabricated, roof, whatever they're called, valances or whatever. But, sometimes we need to write custom stuff, but I do assume you haven't seen programming before. So when I ask questions like that, how many of you have written something in Python? Most of you in your head, you might say, what's Python? And that's fine. That's the expectation I have. All right. So looking through a different lens here, there are 3 kinds of programming languages. We have functional languages, we have procedural languages, and we have object-oriented languages. We are mostly going to ignore functional languages for right now. All right, so I'll just give you, how many of you in any of your math classes ever had like a Texas Instruments graphing calculator? Some point you had a class where you had to have one of these, fancy calculators and you learn how to do 2 or 3 things with or something like that. Well, built into those calculators, there's also a programming language. And it is a functional based language where you might write tools so on a graphing calculator, you have a whole bunch of functions, almost like our magic tricks that we've talked about with our processors. So built into the tool, you have a function that knows how that given an input value, it knows how to take the sine of that value, or the cosine of that value, the tangent of that value. Some of the newer ones, fancy ones, can do derivatives or integrals or whatever. You have functions built into the calculator that do a lot of these things for you that you might want to do, which realistically for a lot of you probably did you a disservice. Because sometimes what will happen in a math class is you'll get really good at using your calculator and not actually learn how to do the math. How many of you have ever been in a math class and you really didn't know how to do it, but you were able to put in the question to your calculator, get the answer, and then reverse engineer the work? Kind of know what I'm talking about? All right. So now in the moment, especially if you're sitting in the middle of an exam, maybe that's kind of a good thing, right? Let's get the answer. Let's get the points. Maybe I'll learn how to do it later, but probably not, right? Because we're people, we just want to get things done sometimes, and that's the way it is. But really, that calculator, from a learning math perspective, did you kind of a disservice there, right? By allowing you to get a correct final answer, it then allowed you to work backwards to fabricate work, whether it was correct or not. Ultimately getting presumably the points or most of the points for the answer, but you actually didn't learn anything. So now you're missing a skill that maybe later on you might be asked to apply to something else. And because you don't have that skill and your calculator doesn't have that more advanced skill, you now can no longer do it. Make some sense? Same thing's true with kind of computer programming today. A lot of folks go to, they either, use like Code Academy or something like that on these websites. or they go to coding boot camps. There's lots of places that are just about, hey, we're going to teach you how to program. And the thing is, I don't want to necessarily say those things are worthless, because they're good for giving you more examples and good for drilling. But what they're effectively doing is they're acting kind of like that calculator. They are teaching you enough stuff to do a very specific type of programming. You know, a lot of them are doing, web-based programming, whether it's, some of them use something called Ruby on Rails, but in any case, they're taking kind of a lot of them are web developer type of problems. And they're saying, okay, well, we're going to go through and we're going to create an application as a group. And we're going to teach you how you could make that application by example. So when you're done with that, yeah, you might have some programming skills, but you only now have the skills that you could apply to problems similar enough to what you just did in that course. And you don't have the foundation to bridge out too much from there right away. Now, that doesn't mean that you can't get there, because now you can go and self-educate yourself. There's tons and tons and tons of Google, YouTube videos out there for doing different things and stuff like that. So the information is out there, but it's going to require a lot of heavy lifting on your side of the coin. You're not going to come out of a boot camp and say, oh, I just squeezed a 4-year computer science degree into a 6-month boot camp, no problem, no harm, no foul. I might even make the argument that when you come out of a boot camp, you actually might be better at doing a couple of things than you would be at the end of a 4-year computer science degree that maybe you didn't focus in on that specific area, but you won't have the problem-solving background to solve problems that you haven't previously seen. That makes sense? All right, so I'm a big advocate of like Code Academy and stuff. These are great places to go and practice and learn stuff, and but I'm also an advocate of, especially when we get into Unity next semester, just going out and following some Unity tutorial on, there's little ones for making like kind of a tiny video game, probably takes you 2 or 3, 4 hours. And it takes you through kind of the simple things of making a Unity game where you have this ball that's rolling around and picking up coins and stuff like that. And you get some primitive abilities that you could apply to a lot of other video games at that point in time. But if your game requires anything outside of those 3 or 4 abilities, you're kind of up the creek. All right, so a functional language is a language that strings a bunch of functions together to solve a problem. Oh, another thing that I'll just let you know about ahead of exams. I don't write the exams typically until like maybe the day before the exam. But what I'll do is the class before you're taking the exam, I will go through my slides and I'll tell you what things I'm going to basically do the same process I do when I write the exam. I go through the slides. I'll say, oh, I think this is something that's fairly important. I'll tell you, I think this slide is fairly important. So you kind of expect a question revolving around that slide. I'll also say, hey, this is good background knowledge, but not something I'm going to test you on. Okay. And realistically, a lot of the stuff we've talked about so far, I don't want to say all of it, because like some of these programming language things like we're talking about here might be important, but a lot of the stuff we've talked about, like the history of the operating systems, I'm not going to test you on those. Okay, but they're an important foundational piece that's going to take us where we ultimately want to go. But I will tell you that I'm not going to test you on it when we go through the slides. So again, try not to freak out with the amount of information I've thrown at you so far, because I would say 90% of it so far is not going to show up on an exam, but it's going to be required foundation for you to keep building your skills on top of. All right. So for right now, I'll even just tell you one of those things right this second. There will not be anything on any exam for the first 2 coding classes dealing with functional languages. They are just different. They're actually really fun. Our language theory class, CSC200, that some of you will take, where we write a programming language, we use this language called Scheme. It's a very tiny language that forces you, and you implement a more high-level general purpose programming language using this tiny old functional language. It's kind of a fun thing, but these are not languages you will commonly run into. So really, when we talk about being a computer programmer, you're mostly living in this world right here. And this world right here is actually strongly related to each other, and we're going to try to demystify something here. Now, any of you who've ever looked into computer programming at all, you maybe haven't seen the word procedural programming before. But I'm guessing at some point you've seen somebody really talk about object-oriented programming, or you've seen something like OOP, something like that. When somebody describes a programming language, so again, I don't expect that you've heard of this before, but if you've ever looked into programming languages, you will probably have heard them reference a language as being an object-oriented language. All right. Well, what we want to do is we want to talk about, what does that mean? What's the difference between a procedural and an object-oriented language? Because in here, we're going to be using an object-oriented language starting day one, yet we're going to be writing procedural programs in it for a while. So procedural programming languages, really, let's not even talk about it from the programming language perspective. That'll make sense in a second, but procedural programming. Code tends to be monolithic, where everything is in one big file and relies on code that was defined higher up in the file. I'm going to probably call that about a B- explanation. Without having a firm example, I can't really maybe do much better than that. But effectively, when you think of procedural programming, I'm going to give you an example here in a few minutes. When you think of procedural programming, I want you to think of, kind of a giant file with code all over the place, almost maybe what you imagine a complex program might look like. It just looks like gibberish, right? Now, I like to talk about the difference between procedural languages and object-oriented languages using an example. Now, what's funny is I've used this example for years and years and years, and it's become, I don't know, like less effective over the years because of how technology has changed. But I'm going to go ahead and use it anyways because it's fun. How many of you have ever used a standard telephone that has a dial tone? 2.5 people. It's like, what's a dial tone? Back in yesteryear, you used to pick up the phone and you hear a dial tone on it, and you push buttons. Actually, before that, you did this little swirly thing. You have to build up the callus. Yeah, you do the thing. A 1 would be that, and a 7 would be that. So you'd hit the number, but you'd and they'd make little clicking sounds. There's actually a famous hacker who built this whistle for hacking a pay telephone phone booths, as if they exist anymore. But how many of you have ever been in a real phone booth with a phone that has a dial tone on it? You see him in the Harry Potter movies. Come on. But anyways, those old phones, this is like a computer network, right? Okay, but the phone network was called a POTS, plain old telephone service network. Well, it actually communicated using sound. It was an analog-based communication. So what this guy did is he created this whistle that allowed him to blow the different tones that it would make when you put quarters into the payphone. So he was able to make phone calls wherever he wanted to go. Making phone calls used to be an important skill, right? Now that your smartphone can make phone calls is really a feature you don't necessarily even care about or use as often as you might, right? Usually we're chatting, we're putting stuff on social media, emailing, whatever. I mean, we still make phone calls sometimes, but that used to be the only way we would communicate. So imagine all the things that you do to communicate electronically, you would do completely through a phone. Well, also cell phones didn't exist. So you weren't just walking around with your communication device in your pocket. You had to go to a venue, either a payphone out in the street or back to your dorm room where you had your phone. And in the earlier days, the phone was tethered to the wall. Then we had wireless phones that could go kind of like maybe throughout your house, that kind of range. But in any case, using those old school phones as an example, but you could also translate it into your smartphones. Let's say you walk into the classroom today, and I have a table up front here. And on this table is this giant pile of wires. All right. It just looks like geeky junk. Right. And I tell you, this is a telephone. And you walk up and you start messing with it. You find some different pieces. You pick up the thing. You hear the dial tone, whatever. That's where the connection is. You hear this dial tone. Finally, you're convinced that this pile of wires is in fact a phone. Right. The reason you didn't immediately believe it was a phone because it didn't look like this. Right. We identify things as objects. We know what a phone object looks like. We know what a laptop object looks like. Sometimes we'll be introduced to a new object. We're like, oh, what's that? But we have a big vocabulary, if you will, of things that we know of by seeing them. You see a car on the road, we know that's a car. Some of us are car people. You might even be able to identify the make and model or whatever. But in general, most of us could identify the difference between a car and, I don't know, like a soda can. If I say point to the car, you can probably make that distinction, right? Because you know what cars look like, what soda cans look like. So this pile of wires up here that in actuality is a functional phone is the procedural version of a phone. You see all of the details, the stuff that you need to use and the stuff that you don't need to use. When you pick up your smartphone, you believe there's a whole bunch of inner working complexity stuff inside this, right? We all know there's some smart people put together this crazy thing, and inside this case, there's stuff that we don't want to or need to understand, right? Same thing with your car. You don't need to know how to build a car in order to drive a car, right? That kind of stuff. So if we were able to see all the details, plus, well, let's just say if we are able to see all the details, we're really dealing with the procedural version of something. So I'll put that as a little caveat. We see all of the details, including the parts we will never need to interact with, sitting in the open. And then I'll put a little thing, telephone as a pile of wires from class example. All right, makes some sense? So now what I'm going to do is I'm going to tell everybody to close their eyes. I'm going to come up front here. I'm going to shove all those wires into this little box that looks like a phone. And then I'm going to say, okay, open your eyes. I'm going to say, what's that? And you're all going to be able to say, oh, that's a phone. So now it looks like a phone. That's an object-oriented language. It's effectively Tupperware. An object-oriented language gives us a level of organization above procedural languages that allows us to hide many of the details inside of the object and only expose the portions of the code that are needed to interact with the object. That's the way we think about the real world. You walk in and you see the pile of wires, you don't even know how to interact with that. Even after I tell you it's a phone, you're still at a loss. Because when you think about a phone, you're thinking about the the things you usually have to do with the phone, right? You got your on switch. You expect to have, I know our phones now have all the touch screen stuff, but you expect to have some way of inputting, hitting the buttons and that kind of stuff. Those are the public interfaces, the part of this device that you will need to regularly interact with in order to make this object work, in order to take advantage of this tool. All right. In a procedural language, all of those things that you need to interact with, plus all of the things that are important, but you'll never actually directly interact with after the thing's built, are all just exposed. Object-oriented language, we hide those details. They're still important, but we stuff them. Once they're working, we stuff them inside the object, never to see them again unless we need to go in and make some tweaks. Then we rip the phone apart and go into the wires and start making some tweaks, but we hide it inside there because we're trying to just be organized, right? Okay, we hide it inside there, and we only expose the portions of the code that we're going to need to interact with to use that tool that we've now built in software. That makes sense? That's an object-oriented language. It's just an evolution of procedural languages, and it's evolving more towards the way human beings think about the real world. We're going to keep seeing over and over and over again how technology tries to mimic things that human beings are already used to. We've seen this over and over and over again. In our conversation so far, where we say that, well, a human being is not willing to meet a computer halfway. We're going to learn how we could do that if we wanted to in here. So again, you're going to get uncomfortable when we start learning about binary and octal and hexadecimal. These are important things, I promise you, that are going to come up in your computer science education, understanding what's happening under the hood. But it's not something you're going to run into every Wednesday. All right. But the thing is that we're not willing to drop down to the computer level. We're willing to come like 0.5% towards the computer side of things. So we'll go a little bit geeky because then it makes us look smart that we can do this geeky technology stuff. But realistically, we want to mostly still be a normal human being that's already used to problem solving in the real world. We're just willing to be a little bit computer geeky so we can talk to this guy here. Make some sense? Which means that we need tools provided to us by the computer itself, the operating systems, and the programming languages that meet us 99.5% of the way towards being a person solving a problem, so that we can actually tolerate dealing with this thing. So even though we could technically punch out zeros and ones to write code for a computer, it's possible. There's a rhyme and reason to those zeros and ones, and we'll talk about that to a certain extent. We don't want to, and we'd be very error prone as human beings doing that. So we want there to be tools that sit between us and that to allow us to make our lives easier, because our lives are already going to be hard enough as it is learning this stuff. That makes some sense? All right. So, and frankly, what has shocked me over the years is I don't know if I've ever seen a textbook be able to truly describe the difference between procedural languages and object-oriented language in terms of what it really is. It's Tupperware. It's going to Target and buying a couple of things to organize stuff and putting a piece of tape on it and says, these are my tax documents, or these are my old shoes, whatever. It's an organizational tool. They've given us the ability to stuff stuff inside this object that in these languages is usually called a class. You can build a class, you can stuff all the wires into it, you tie it off, and you poke a couple of holes that say, okay, those are the parts I need access to. Object-oriented programming. That's it. As opposed to, here's the wires. It works, trust me. All right. That makes some sense? All right. So now let's get geeky. What's binary? going to call this number basis. So what's the number system we use? We use decimal, right? 0 through 9 are the numbers we use to make all of our numbers. So decimal. So if we think about the decimal number system for a little bit here, I want you to think about this as a language. It's a language of numbers, okay? So any number you ever write using the decimal system, you write in terms of the digits 0 through 9, right? Okay. And this is base 10. 10 fingers, 10 toes, yada, yada, yada. All right. What's binary? Go ahead.
Ones and zeros.
Ones and zeros. So every binary number that you ever write, and you don't even have to know what that is yet. You're going to know really quickly, and you'll eventually like it. You have to, because there will be a conversion question on every single Litman exam you ever have, even outside of this class. And after you learn this stuff, it's going to be free points. All my exams are 10 questions, 10 points each. Effectively, after you understand how this works, it should be free points on the exams. And it won't be, and then I'll make fun of you. But eventually you'll get it into your head that, oh, I should just actually learn this pattern and get my free 10 or even sometimes 20 points on an exam, just converting some number between binary and decimal. All right. So binary is another numbering system. We can almost think about it as like another language. Instead of English, is German. Okay. And all the numbers that we write in binary, we write with zeros and ones. Here, I'll keep this the format standard. 0 to 1. Okay. That's our entire, just like English, our alphabet is A through Z. And you got some other, we got the Klingon. You know, that is official language. You know, Klingon, we'll actually, I'll have an example with Klingon that actually fits here before long. Maybe not today, but maybe Tuesday. Oh. Pause for 1 second, just so I don't forget. And I'm going to tell you this multiple times as we come up to it. The first week in October. So I think it'll be October 4th, 6th, whatever it is. The Tuesday, Thursday on that week, and the Tuesday and Thursday the next week, I'm actually not going to be here. There's 2 things I'm doing. I have a conference in New York. And then I'm going up to Canada to my wife has cancer, so I'm going to a cancer specialist up there. But class won't be canceled. Instead, I'm going to bring in somebody. If you've been at the university for a while, you've probably met him before. His name is Waleed. Him and I do quantum computing research, and he's going to do like a 4-class series on quantum programming. He's going to first teach you what quantum is and that kind of stuff. But hopefully when you come out of that, you're going to see pretty clearly that, oh, it's just programming. Because remember, day 1 of class, I said, programming is a skill set. The language doesn't matter. But in any case, I just wanted to preheat you to that. We will still have class. I just won't be the one sitting here. I will have access to email and things like that. And unfortunately, the timing is weird here, but it's hard to get into cancer places. So it is what it is. And, you know, hopefully you're cool with me choosing my wife over you guys for those couple of weeks. But in any case, I think it should be a cool experience anyways in class, but just be prepared for that. It's kind of if you haven't followed quantum stuff at all, it is. How many of you have ever heard anything with quantum computing? How many of you heard the phrase quantum computing? Okay. Anybody roughly know what quantum computing is? Go ahead.
Being able to have 0 and 1 on at the same time.
Okay, so that concept in quantum is called superposition. So quantum computing is, I'll just give you the 5-minute version of it, because now that we're on the topic, because it is freaky deaky, and some of you won't sleep again after you hear this. But it's computing based on something called quantum mechanics. So what is quantum mechanics? So how many of you have heard that phrase before? Quantum mechanics. Probably don't know what it means, but you've heard the phrase, right? So effectively, when we say quantum, what we're talking about is really, really, really small things you would see under a microscope. So for instance, we have light coming out of these lights, right? That is a stream of these things called photons. So you can think of photons like little tiny marbles, right? But they're microscopically tiny. We can't see them with the human eye, but we know they're there, right? So there we are all being bombarded with a whole bunch of pieces of matter called photons that pass right through us, right? But they're physical things. So really, when you think about a photon, think of it as the same thing as a tennis ball or a basketball. It is a physical piece of matter. It's just so tiny, we don't really interact with it. Make sense? So quantum deals with that world, the world of the ultra tiny. And this is where things get freaky. So now, if I had a basketball and I tossed the basketball at you, you would catch it and, whatever. If I tossed a tennis ball to you, it's a different object, smaller object, but behaves the same way, right? So we would translate that into, okay, well, it doesn't matter how small an object gets. It is always going to kind of behave like a piece of matter, right? It's going to behave the same way. It just is smaller. You wish it was that way. So there's a famous experiment, and I encourage you to maybe go, Wally will probably show it, but if you want to really scare yourself, look at it online. There's all sorts of cartoon animations on YouTube about it. It's called the double slit experiment. And effectively what it is there's like a wall like this, and they put a cardboard thing in front of it with two slits in the cardboard. And what they do is they shine a flashlight. So they're standing on that side, they're shining a flashlight through those slits and looking at what shows up on the wall here. Now, back up for a second. If we had the accuracy and you threw that tennis ball through one of the slits, we'd expect the tennis ball to bounce off a single point in the wall, right? That's how matter works. But no, instead, what we see is this whole bunch of different, it's called an interference pattern. So we see this like line of light hitting the wall. So now you're throwing the single tennis ball, piece of matter, a single photon through that slit, but it's hitting everywhere, not that one spot. So that seems weird right off the bat, but that's not the freaky deaky thing yet. Well, so the scientists who originally did this, they thought, okay, well, maybe, because they're shining a flashlight through it, maybe we need to slow it down and we need to come up with a machine that can fire exactly one photon, one tennis ball at a time, instead of turbo speeding the tennis balls, right? Because really what we're talking about right now with a flashlight is you have like one of those tennis ball machines that's just firing 600 tennis balls one after another through the slit, and maybe they're kind of banging into each other or whatever, and that's what's causing it to hit all sorts of different places. So they came up with a machine that fired a single photon, one tennis ball, same interference pattern. It's like, okay, well, wait a minute, why? So you're asking the question why, and it's always that. It's always a single interference pattern, which would definitely be different than us throwing that single tennis ball through there, which would just hit the wall, right? So they decide, well, let's take a look and see what's happening as that photon is flying through there. We want to know what's actually occurring. So they set up a camera to look at it. As soon as they observed it, as soon as they decided to look at it, it started behaving like a particle again. They didn't change the experiment at all, except they looked at what was happening to that photon as it was flying through the slit, and all of a sudden, like a kid getting caught with his hand in the cookie jar, it was a single dot on the wall instead of the interference pattern. I don't know. To me, it's kind of like almost evidence of a creator or something like that, where these little quantum things are floating around down there, and they like, they're too cool for school, and because like, oh, we're so small, nobody can see us, and I was like, whoop, wait a minute. I mean, that is freaky, right? And so only thing that's different there is you are looking at it. You're not touching it. You're not doing anything. You just looked at it and it behaves differently. So, and you've probably heard this reference before on TV shows. I referenced Big Bang Theory last class. So there's that something acts as a particle instead of a wave. That's the thing they're talking about here. In this case, it acts as a wave when you're not looking at it. It acts as a particle when you are. Is the punchline. But you're not touching it. You're just looking at it. And they tried to break this by almost like doing like a sneak look. They tried all sorts of different experiments when they were trying to pretend like they weren't looking, but kind of just getting always changes its behavior when it was observed. So quantum computing is based on this quantum mechanics thing, which can kind of be encapsulated in that little story, right? And this is related actually to what I talked about earlier today, in that I'm calling it kind of, when we talked about like using your graphing calculator in your math class to solve the problem for you, I kind of referenced that as a bad thing, right? Like you're not actually learning the math, you just learned how to use the tool to solve the problem so you can get your points for your answer, right? Well, with quantum, we understand what to expect. We see the result and the results are consistent, but we don't necessarily understand why it behaves that way. But it always behaves in a certain way. So our quantum computers that we're every single month, our quantum computers get more and more powerful. The two big leaders in it right now are IBM and Google, making these quantum computers. And as soon as we hit something called quantum supremacy, which means these machines have enough what's called a qubit in it. You mentioned that instead of just being a 0 and 1, it could be both. A qubit is like a bit inside of a computer, but it can be 0, 1, or usually people will say or both, but really it's 0, 1, or anything in between. So you can think of it as like a sphere where it can literally hold any value. Any value. And if you have enough qubits, you can represent all things all at once. And this is where we run into this is going to be a big news thing in the next, frankly, it could happen next week, or it could happen 2 years from now. As soon as one of these physical quantum computers has enough qubits in them to represent general problems, and where the first general problem we would look at is, how many of you have ever bought something online and had to put your credit card in? Most of us at some point, right? At some point, if you bought something off Amazon, you put your credit card in at the first time, right? Okay. And you look for that little lockbox, right? The little padlock thing on there, because that tells you, okay, I'm good, right? That I'm secure, whatever it means, whatever's happening under the hood, it's protecting me. Well, that encryption is what it's called, is based on our modern day encryption technologies, which assumes that the tools you might be using to crack that encryption, to break, to find out what your credit card actually was, is one of these normal computers, or even a whole bunch of these normal computers working in cahoots. Okay, and usually this is called a brute force attack. So you can think of a brute force attack as, there's a lock on this door over there, and you have 4 zillion keys, and you're going to try one key at a time, right? Until you find the one that fits. Okay, now, if we say, let's use a real number, 4 trillion. We have 4 trillion keys. How long would it take you as a person to try 4 trillion keys? We'll round down and say a ridiculous amount of time. Okay. How long would it take a computer? We'll round down and say a ridiculous amount of time, but less time than you. Okay. Well, now let's take 5,000 computers and we divvy the keys up among those 5,000 computers. We have them each working on it. Again, rounding down, a ridiculous amount of time, but less time than it would have taken one computer, and less time, which is less time than it took you. Our modern encryption algorithms say basically by any brute force attack that we use today, it would roughly take 3 trillion years for a brute force attack to work. Now, hey, you could hit the lottery and it might be the first key you try, right? Could happen. But generally speaking, the average amount of time is 3 trillion years it would take to crack your credit card number. We feel like that's pretty secure, right? We're all good with that. The problem is the algorithms for doing brute force attacks on security stuff already have been written for quantum, because when he shows you how to write quantum programs, you're going to be using a language running on, I'm guessing he's probably going to use IBM's thing called Kismet. You're going to be using a language that they're emulating. That language is running on a normal, these are called classical computers in the quantum world. It's running on a normal computer. It's just pretending to do quantum stuff because we know how those things behave up to a certain number of qubits. But when you have a physical, actual quantum computer that's using actual qubits, now you get the real power from this. So that exact same model, once we have, I think the number is 2048 qubits is what they've decided is quantum supremacy, which means that you now have enough actual qubits. And these are hard to build. That's why they haven't come up with them. Like an actual qubit, I mean, it deals with something called quantum entanglement. There's a lot of stuff involved there. It gets crazy, but it's not something they can just send off to Sony and say, make me one of these. It takes it's really difficult to entangle, subatomic particles. We're talking about weird, freaky deaky stuff here. But in any case, once we have, I think it's 2048 of them, you now can solve generalistic problems. For example, that problem. So now instead of your credit card being safe, but unless somebody has 3 trillion years to work with, it now turns into something like 5 to 10 minutes overnight. That's a problem. 5 or 10 minutes isn't that long. If somebody could have your credit card number in 5 or 10 minutes, instead of 3 trillion years, you might be concerned, right? And then move that outside of the world of credit card numbers or something and into some other things. But, this is where things are going with quantum computing. And it's knocking at the door. People are actively working with this right now. The way the quantum computers work is effectively they represent every possible state of something inside of one of these qubits. And then when you observe it, it collapses down to a single answer. Kind of like that, the double slit experiment, where when they observed it, it turned into a single thing. When you weren't observing it, it was a whole bunch of stuff. Make sense? So it's roughly based on that concept. All right. So quantum's really cool, but super scary and kind of thought-provoking from a creation perspective, in my view. Kind of bothers me that if I look at a subatomic particle the wrong way, or even at all, it behaves differently than when I'm not looking. Man, isn't that freaky? All right. So in any case, I wanted to give you the long-winded heads up that the first 2 weeks of October, we will have a guest lecturer, but it'll be good stuff. If it's not good stuff, it's not my fault. All right, so we're talking about our number bases. So binary, you told me zeros and ones. These guys are called bits instead of qubits. All right, so decimal, these are called digits, and that's base 10. Binary, these are called bits, and that's base 2. What about octal? How many of you have ever heard of octal? Okay, what's octal? Heard the word. Anybody know what it is? Go ahead. Base 8. Okay, so what's the language of octal? What are the they're called octets in this case. What's the language of octal? If decimal is 0 to 9, binary is 0 to 1, what's the language of octal? 0 to 7. All right. So notice decimals base 10. The legal digits are 0 to the base minus 1, 0 to 9. Binary, base 2. The legal bits are 0 to the base minus 1. Same as the pattern with decimal. Okay, so it's 0 to 1. Octal, base 8. The legal octets are 0 to the base minus 1, which is 7. So these guys are called octets. This is base 8. Okay, then we have something called hexadecimal. Hexadecimal, these are called hextets. Hextets. And this is base 16. What is the language of hexadecimal? Okay, so 0 to 9, and then A through, in this case, it's F. So basically, this is 0 to 15. But, you know, we can't put a 10 in here. We can't say 0 to 15, because if we have a 15, is that a 15 or is that a 1 and a 5? Make sense? So you got to have a single symbol representing the language of this thing. So we have 0 to 9, and then A is a 10, B is an 11, C is a 12, so on and so forth. Okay. And these guys officially are called hextets. Now, realistically, we can say, what are the digits of the binary system, 0 and 1? The digits of the octal system are 0 to 7. The digits of the decimal system are 0 to 9. Digits of hexadecimal, 0 to 9, A through F. If you call them digits, everybody knows what you're talking about. But officially, these are bits, octets, digits, and hextets. All right, for these different bases. We're going to call these the popular computing bases. All right. These are the popular computing bases. Now, before I go any farther, I'm going to give you another homework thing. Write a 2 to 3 page paper. Again, we'll see if we improve from our first ones. On the, let's see, on why the numeric bases 2, 8, 10, and 16. So I can put in parentheses. This is binary. This is octal, and I'll put this up on Blackboard too. This is decimal. Ooh, butchered that. And hexadecimal are common bases used in computing. So why are those 4 common in computing? Each one kind of has its niche. Okay, I'll even start you off. Decimal, it's because when we talk about computing, we're involved, right? And we like decimal, 10 fingers, 10 toes. We're going to be speaking the decimal language as often as we can. And this guy's got to put up with it. All right. But ultimately, under the hood, binary, octal, and hexadecimal play roles in computing. So the goal of this paper is to have you research what those roles are. Make some sense? All right. And I'll put this up on Blackboard after class today, but I just didn't want to forget to do that there. All right, so here's our number bases: binary, octal, decimal, and hexadecimal. You can certainly have larger bases. You can have bases up to base 36 using the English alphabet, right? You know, because you can go 0 through 9, then A through Z, right? So base 17 would be A through G. Makes sense? Base 15 would be A through E, so on and so forth. You know, so we're just using the letters of the alphabet to represent single character representations of another number. All right. So those are our different bases that are available to us. Now we have 2 patterns for converting between bases. Any base to decimal, and then decimal to any base. So there are two patterns that you need to learn in order to convert between any two bases, regardless of whether they have fancy names or not. Because you can have base 3, base 4, base 5, base 6, base 7. They don't have fancy. Well, they probably somewhere behind the scenes there probably are mathematically official names for those. But in terms of what's commonly talked about, only those 4 have names: binary, octal, hexadecimal, decimal. Okay, but any base is allowed up to base 36. After that, we have to start there's nothing that says these patterns still work for bases above 36. We just have to come up with more letters to represent our numbers, right? So maybe you have all the lowercase letters be your, first set, and then all the uppercase letters be your next set. You can say, okay, well, that works. The joke I was making earlier is years and years ago, we thought, well, what if we use Klingon? Well, Klingon only has 22 characters in it. It's actually worse off than English. But now if you tack Klingon onto the end of Klingon is a language from Star Trek, by the way. If you don't get that reference, I have to think about the age of the audience at this point. Things keep changing. You could take the English alphabet first. You get your 26. Then you can tack on Klingon after that. Okay, and you get another 22 bases, after that. So now you can have base 58. Something along those lines. You get what I'm saying? So as long as you can define the characters you're going to use to represent things above 9, you can make these patterns work for any size number. And you're going to see kind of the advantages of these as we go along. Like why use hexadecimal as opposed to binary in some sort of situations, that kind of stuff. But in any case, as a general rule, English is the language that's used for the things, and we really don't have common needs for bases above. I would say that we're getting to the point now where bases larger than 16 maybe start making sense, and we'll talk more about that, but not much bigger than that. So I think 16 still has us in a decent spot, and you'll understand why once we get to it. But so at this point, we don't need to be overly concerned about having more letters to represent numbers, because we really don't have a great use for that other than just, morbid interest or something like that. You go back to the dean talking about like Lippmann's making us learn Klingon. Is this acceptable at Concordia? Big Bang Theory, they all speak Klingon to each other, by the way. All right, so these are the two patterns we need to learn. So one pattern allows us to convert from any base, doesn't matter what it is, to decimal, to a number system we like. And there's another pattern that lets us takes our number system, decimal, and convert it to any of these other bases. All right, so let's start with this guy. So let's go from any base to decimal first. Okay, so 10110 from binary to decimal. All right, so this is from any base other than decimal. Actually, you can use this pattern to convert from decimal to decimal. I'll show you that. It's a waste of time, but you could do it. The pattern works, right? All right, so that kind of shows you that once you know these two patterns, you can show off to your friends how you can convert. Well, you don't do that? You don't sit at the dinner table say, hey, you want to know what that is in octal? You should. All right. So this particular pattern, you do is you write out the number first. Now, once you get kind of good at this, you'll be able to do smaller numbers like this in your head, but let's really spell it out. Okay, so I put some spaces in here so we can label them with the numbers we need. So we are converting from base 2 to base 10. All right. So since this number is currently represented in base 2, and now keep in mind, somebody needs to tell you that this is a base 2 number, right? Because isn't that a legal decimal number? That's 10,110, right? We can read that. But I'm telling you that's a base 2 number in this case. So we're only using the bits, zeros and ones, to build this number. But it just so happens that those are legal bits in octal, hexadecimal, decimal, doesn't matter. So somebody does need to give you some information about what the representation currently is. So we're saying this is a base 2 number. Since that's a base 2 number, let's see, 0, 1, 2, 3, 4. This is 2 to the 4's power, 2 to the 3, 2 to the 2. Ooh, look at that. 2 to the 1. I do question, why didn't it automatically fix that for the other ones? All right. So really, you start from the right. This is 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4. The next one would be 2 to the 5, 2 to the 6, 2 to the 7. If this was an octal number, this would be 8 to the 0, 8 to the 1, 8 to the 2, 8 to the 3, 8 to the 4. All right, for what those places are. Okay, so now let's do the math. This is the 1's place, the 2's, the 4's, the 8's, the 16's. So this is the 16's place. This is the 8's place. This is the 4's place. This is the 2's place. This is the 1's place. Any positive number to the 0th power is the number 1. So the far right value in any number you're converting will always start off at 1. Times 2 is 2. Times 2 is 4. Times 2 is 8. Times 2 is 16. Okay, so usually you won't think about it in terms of that, but that's the pattern. With those 2's to the power. 1 times 2 is 2, times 2 is 4, times 2 is 8, times 2 is 16. If this was base 8, we'd have 1 times 8 is 8, times 8 is 64, so on and so forth. Okay, same pattern. Make sense? So now what we do is we do the math. 1 times 16 plus, we could skip the zeros because 0 times anything is 0, but we'll put it in there. 0 times 8 plus 4 times 1 plus 2 times 1 plus 1 times 0. I'm sure I can do that in my head, but just for time's sake, let's just do this. So that, do I have bad? Why didn't they give me my answer? What is it? 16 plus 4 is 20, plus 2 is 22. So this is the number 22 in decimal. So 10110 in binary is equivalent to the number 22 in decimal using this pattern. Make some sense? All right. So homework for next class. Again, try to do a little deeper research. I would say in general, people didn't go into enough research for that first paper, because I'm going to ask you when we come back to class, help me understand, when is octal used? Binary, we kind of sort of know the answer-ish. That's that computer level, but when's octal, hexadecimal used? So really try to find those answers. Make some sense? Yeah. All right. I will see everybody on Tuesday.